So we're going to go back, and I'm going to put this in black. Let's see. This is blue. This is blue. So this is. I forget the order I did this, but okay. So this is not there. This is blue, and this is blue. Okay. So we've done some number of steps, and we've done I steps, and after I steps, our subsolution. Not exactly. This is easy for trees. It's not okay. So after I steps, we assume that we've discarded the blue vertices, making these blue now, and we've added the red vertices to our vertex cover, and there is some way to process the rest of the tree such that we get a minimum vertex cover. So our subsolution can be extended to an optimal solution. But now, what do? We take, let's say, yeah, I think we considered this leaf next. And we took this vertex. So we took this vertex. Now suppose that we make this decision, but our subsolution can be extended to an optimal solution S, but S takes this one. So, no, we were green and S was blue. Okay, so S is going to take this. That's blue. Not sure you can see that, but it's blue. Now, we have to say, oh, S does something else at the I step. We consider some vertex, we consider this vertex, and we take this one. But S doesn't take this one, it takes this one. Well, what can we argue? How can we argue that when we take this one, it can still be extended to an optimal solution? Well, we take the green one. This is a leaf. So okay, maybe it's not a leaf, and maybe it didn't start as a leaf, but all of the other edges that were incident to it are already covered. So we don't have to worry about that. So this is a leaf, so it's only covering this edge. When S takes this leaf, it's only covering this edge. When we take this vertex, it's covering this edge and possibly some other stuff. So suppose that this is looking purple because it had some red there, but it's blue. I'm going to use a different blue. Is this a stronger or weaker blue? It's just a different blue. Okay, so let's suppose that, so S would have to take this one in order to cover this edge if it didn't take that. So let's suppose that the blue stuff, apart from the blue stuff, is the rest of S. So S took the red stuff, and then it took the blue stuff, and we took this green one. We took the red, and on the I plus first step, we take the green one. Well, notice that this one is just covering this edge. This one is covering this edge, and possibly some other stuff. So the rest of S's solution is compatible with the green one, with not taking this and taking this, because all that changes is which endpoint of this edge we're covering. So with S's solution, without the green, we had to take this to cover this edge. Actually, we would also have to take this, because, okay, so maybe we're going to take that as well. But if we move sort of a marker from the leaf to what was the green, then we'll be covering some edges twice, but that's allowed. Okay, it's not a problem that we cover edges twice. We just have to cover everything at least once. So we can do this switch, this exchange, and then so we're going to uncolor that, color that. It's still compatible with the rest of S's solution. So we haven't increased the number of vertices we're taking. It took this, we take this. That's both one vertex in either case. Our solution is now compatible with the rest of S's solution. We're still covering everything that S was covering. So our sub-solution after I plus 1 steps can be extended to an optimal solution S prime. Therefore, by induction, we get an optimal solution. Okay? Because of time, I forgot to reset this. No. Okay, I'm going to assume that 5 minutes passed. Oh, 6 minutes, but that's okay. So I'm going to skip the argument for why you can do. I wanted to show you the approximation algorithm on graphs because it's a hard problem. So when you're faced with one of these hard problems that we don't know how to do, one thing you can do is say, oh, well, maybe you can actually just do it in practice. Like, maybe it's not really that hard in real life. It's only hard on these orchestrated, really pathological instances. And so you can just try it. And you won't have good bounds, but maybe it works okay in practice. The other thing you can do is say, well, maybe the general problem is hard, but I'm not working on the general problem. I'm working on trees. I'm working on planar graphs. So a lot of stuff is hard for planar graphs. A lot of stuff that's hard on general graphs is also hard on planar graphs, but sometimes it's a bit easier on planar graphs. For example, coloring. It's still hard, but it's not as hard, we think. But sometimes some stuff is actually easy on planar graphs, and a lot of stuff is easy on trees. And actually, as somebody said, somebody mentioned dynamic programming. You can usually use dynamic programming to do stuff on trees. We're just doing greedy at the moment. The other thing you can do is say, well, I don't think I can get an optimal solution, but maybe I can get a solution that's really close to optimal. So if I get finished with knapsack, I'm going to show you how you get a solution that's at most, a vertex cover that's at most twice as big as the minimum. Okay, but first knapsack. Oh, so I'm going to have to, everybody has access to the scribe notes from last year, when I made the students from last year actually write what I was saying. Okay, so this is, but it wasn't just that I was being cruel. I didn't, last year it was the first time anyone was dealing with online teaching. Well, I mean, some people have been doing this for years, but first time I had been trying to do this. So I didn't know how to do a midterm, so I gave people the option of not doing a midterm and writing scribe notes instead. So it just wasn't just sort of random cruelty. And there's a really cute picture of knapsack in the scribe notes from last year, which I may steal for the lecture notes this year. So knapsack, you imagine you have a knapsack, a backpack, and it has some capacity. So knapsack with some capacity C, and then you have some food items, for example, well, some items. And since this class, I had breakfast, but that was a while ago, and it's lunchtime, so let's talk about food. Some food items. Oh, now I'm going to be really hungry. So I have like nothing in my fridge, but suppose I have some cheese. So you have cheese, you have bread, you have an apple. What else can you have? Cheeseburger. Carrots. I actually have carrots. I have. Oh, so actually, I'm going to leave out eggs. Kool-Aid. Yeah. This is going to be. This is going to be an interesting one. But let's suppose that you have like you have lots of different sizes of containers, so you can choose however much Kool-Aid you want to take. Wasn't in there too long. Yeah. It's hot today. It's like it said it's going up to 24. Okay, so you have some items. Each one has. So for this problem, we're going to assume that I'm just checking. Nobody's trying to join. You're going to have some weight, and then you have some benefit. So let's say you have calories, like how much we like it, the flavor, whatever. Okay, so let's say the cheese, you have 1 kilo of cheese. And 1 kilo, I have no idea how many calories 1 kilo of cheese has, probably a lot. So let's say it's 1,000 calories. And let's say you have 500 grams of bread, but this only has 100 calories. You have an apple, this is maybe 100 grams, big apple, and it has 50 calories. Okay, cheeseburger, let's say a quarter pounder would be like 125 grams-ish. And this is also going to be 1,000 calories. Okay, carrots, you have a kilo of carrots, and but this is only 200 calories. Kool-Aid, let's suppose it's frozen Kool-Aid, 9,000. Okay, 9,000. Okay, let's forget about. I don't know how to deal with the Kool-Aid at the moment. I have a thermos. Let's think of the Kool-Aid separately. Okay, so your knapsack, some capacity. Let's say you can take. It's a very small knapsack. You can only take 1.5 kilograms. It's like a lunch bag. Okay. So, you want to take food, it's going to be a long hike. You want to take the maximum number of calories you can without going over the capacity of your knapsack. And here's the important thing for this problem. You can cut these items, okay? So, you can't go over the capacity of the knapsack, but if you get up to the top of the knapsack and you're like, oh, well, I have a kilo of cheese, but I can only fit 200 grams worth in, then you can cut and just put in 200 grams worth of cheese. So maybe if you get to the top and you're like, I can only take 70 grams of cheeseburger, you can cut the cheeseburger. This is why the Kool-Aid is a problem. Not sure how you cut the Kool-Aid. You can like chop the apple up. You can like chop the carrots. Okay, so how are we going to do this? How do you decide what to take, how much stuff to take, so that you optimize your the calories in your knapsack? Now I'm so hungry. Right, you take the caloric density. Right? So what are we going to take? I think it's going to be the cheeseburger. this is not the optimal way of actually putting it in the knapsack. We're going to put the cheeseburger at the bottom. So the cheeseburger goes here. It's a very rectangular cheeseburger. So now we have a little less than, like, we have 1,375 grams left, and we took the whole cheeseburger, okay? Full of burger and wheat. Yeah, but we only have one cheeseburger. You know, somebody has, some health nut has been free has had access to our refrigerator and thrown away everything. We just managed to hide the one cheeseburger. So, so we only have one burger. So now what are we going to take? So we would actually have to think, this is, so the next best, I think, is to take a kilo of cheese. Yeah, that doesn't, healthy people would maybe, I don't know. So we're going to take a kilo of cheese. So 1 kilogram of cheese. This is actually the kind of stuff I tend to take on my hikes. That's, okay. So this, now we have 375 grams left, because this is 1 gram for 1 calorie. This is 1 gram has way more than 1 calorie. So the cheeseburger is best. Then this is 1 to 1. This is 5 to 1. This is 2 to 1. And this is 1 to 5 to 1. So this, so we could take the carrots, or we could take the bread. It doesn't matter if you take the carrot, but you can only take 375. So let's say you take, oh, let's say that this was 150, so that we're going to take the bread. So we're actually going to take a cheeseburger and cheeseburger ingredients. So this is actually way too. So this is the 375. So we're going to take 375 grams of bread. Okay. So why is this? When we take the apple next, the apple is, oh right, sorry, because this is 5 to 1 and this is 2 to 1. Yes, you're right. Sorry. We would take the apple. Because this has the next highest ratio. I was getting confused. And then we have 275 left, and we're going to take 275 grams of bread. So down to about here, it looks like a healthy knapsack, and then you think, oh, maybe like this and an apple and 200 grams of cheese, and then you realize, no, it's a whole kilo of cheese with a cheeseburger buried under it. So from above, it looks good, and then when you get down into the hike, you actually have the calories. Okay, so we don't have very much time. So I better stop joking around and actually get, why is this the best we can do? Well, before we take any steps, we have this empty knapsack. Our empty solution can be extended to an optimal solution. Let's suppose, how did I do that before? Okay, so I had like our partial solution. So we have taken some items, and maybe we cut them, or, well, we don't cut them until they don't fit. But, you know, we've taken some stuff, and then we take, we're processing these in order by density, and we take something, and let's say that we take this. So before we take any steps, our empty subsolution can be extended to an optimal solution. Suppose that after I steps, our subsolution can be extended to an optimal solution S. So we take the green thing, and let's say that this is S, this is us, and this is S. So S takes the same two things to begin with, but then it decides not to take the green thing. It takes, or maybe it takes a little bit of the green thing, but not all of it, and then maybe it takes some blue thing. Okay? Well, let's just suppose it takes some blue thing. We'll color the blue thing. The blue thing could also be, let's make the blue thing bigger. Let's make the blue thing two blue things. So if we're looking at S's solution, you've got this. Okay. So how do we do the exchange? Well, we're going to take this, which S didn't take, and let's say that this is 100 grams. And now we're going to take, so this blue thing could be 100 and 200 grams. We're not going to throw all, and then it's got some other stuff on top. Okay, I'm going to actually use the new blue marker because desperate times. It's got some other stuff on top. So what are we going to do? We're going to take the 100 grams of this, and we're going to cut. So this is why we need this argument that we can cut. We're going to cut this blue stuff away. And we're going to stick in here the 100 grams of the green thing. Okay? So we leave the rest of it alone. So all we've done is taken 100 grams of whatever this was, thrown that away, and inserted the green thing. Okay. Why do we know that that doesn't reduce the overall caloric load of S's knapsack? Well, because we sorted these things by density. So that means that this 100 grams that we inserted here, it's got more calories than the 100 grams of blue stuff that we got rid of to be able to insert it. Okay? Because it's at least as calorically dense as the 100 grams of whatever was in here. And we know that we can get exactly 100 grams because we can cut the blue thing to be able to fit it in exactly. Okay? So now we take S, we do this exchange, we like exchange an apple for the bread, we like cut the bread in, like cut an apple shape out of the bread, and we put the apple into the hole in the bread, and then we have not decreased the caloric load, so we get this solution S prime, which now extends our subsolution after I plus 1 steps. Okay. We have 4 minutes. So this does not work with, for example, eggs, a jar of pickles, you know, other stuff that you cannot cut, right? Because if you think, suppose that you have an egg. You cannot cut an egg, an uncooked egg. So maybe an egg is the calorically densest thing. So an egg is, what, like 20 grams? And it's, I don't know how many calories, 100 calories. I don't usually pay attention to calories. So it's 100 calories, say, and then, then you have something which is the whole 1.5 kilos of, I don't know, what's something else we can't cut? 80 calories. Are people looking this up, or do you just know this? I was close. Maybe it's a big egg. What's something else you can't cut? You can cut a watermelon, but then it will go bad. So let's suppose you have a watermelon, and you don't want to cut it, and it's 1.5 kilos, and it's 1,000 calories. Okay. So, and this is the only stuff you've got. A container with cuts in it. What? A bottle. Yeah, as I said, a bottle of pickles or something. That's okay. Okay, we're just going to keep going because I think the little camera will have some time left. It has like 3 minutes left. So in 3 minutes, we're going to stop because we're also out of time in 2 minutes. So, okay. If you do this and you say, oh, well, we're going to do this by density. This is the most dense. So you put in the egg. And then, that's kind of it should be more ovoid, but okay. And then because you put the egg in, you don't have room for the watermelon. So the sorting thing doesn't work in the case of binary. So when you're allowed to cut, it's called fractional, because you can take a fraction of the thing. And when you can't cut the stuff, it's called binary. You can also get, I'm not going to have time to do it, but you can also get an approximation algorithm, a greedy approximation algorithm for the binary case, but not doing it by density. Maybe I'll put this on the assignment. But the approximation ratio, again, you can get 2. So you can't get the maximum number of calories, but you can get at least half. Remember, with vertex cover, you couldn't get the minimum, but you could get twice the minimum. Here, you can't get the maximum, but you can get at least half. But not sorting by this way, because this way, you take if you sort by, you can sort by various things, and we actually don't, there isn't a greedy algorithm for doing this. And as we'll see after the midterm next week, when we get into dynamic programming, I'm going to teach you a dynamic programming algorithm for this problem. But it looks like it's polynomial. But remember that stuff about factoring, where you said, oh, well, you can find the factors in linear time. If I give you n, then you can find the factors of n in time O of n. Well, the same thing. You can find the dynamic programming for knapsack, dynamic programming algorithm for knapsack runs in time that's polynomial in the size of the knapsack. But the size of the knapsack, I give you the size of the knapsack, the statement of the instance. I don't write the size of the knapsack in unary, I write it in binary. So actually, this problem, binary knapsack, is NP hard, but it's NP hard in the weak sense, which means that if I give you the instance with all the numbers written in unary, then you can do it in polynomial time in the amount of paper I needed to write that. But if I give it to you with the numbers written in binary or decimal or something, then we don't have a polynomial time algorithm for it. That problem, knapsack, yeah. I always get so there's knapsack and subsystem. I think this one. I think yeah. When you can, I'm pretty sure this one is knapsack. It would be naturally called knapsack. There are versions where you can take multiple instances of stuff. I think this is, I'm pretty sure. I'm thinking